Hi everyone. Last lecture, I introduced the topics of impulse and momentum, and we took a look at some situations where the momentum of an object was changing, and we want to figure out what that implied about the force that has caused the momentum to change and the duration of time that that force was applied over. Today's lecture, we are going to focus on what happens more with objects colliding and the transfer of momentum that can take place. So imagine, for instance, that there are two ice skaters and they're standing at rest on a frozen lake. They push off of each other, and after the push, they both move away from each other. If each skater is moving, then they, of course, have momentum. But where did that momentum come from? This is what today's lecture is all about, interacting objects and momentum transfer.
Last lesson, we learned that the net force acting on an object is equal to the derivative of momentum with respect to time. So imagine that the net external force, so all the outside forces acting on an object, is equal to zero. So there are none. Then it would also hold true that the change in momentum as a function of time would be equal to zero, right? The momentum would not be changing. This is what we're going to focus on today. So let's suppose that, what I had just said, the net external force acting on an object, and therefore the net impulse, is zero. This is described as an isolated system. And there's no particles entering or leaving the system, so this is a closed system. Then the total momentum would remain constant. A mathematical way of writing this is that the sum of the final momentum equals the sum of the initial momentum. That Greek letter sigma means sum of. It means add them all up. Sum as in SUM. Means take all the final momentums of the objects in the system and add them up, and that's going to be equal to add up all the initial momentums in the system. This is known as the law of conservation of linear momentum. So, for example, let's consider this situation. We have two skateboarders that are moving towards each other. The girl, who has a mass of 42 kilograms, is moving with a speed of 1.2 meters per second towards the boy. And the boy, we're told, has a mass of 51 kilograms. When they collide, they come to a complete stop. We're going to use that information to determine how fast the boy was moving towards the girl. So, in order for us to do this, we should figure out what the total initial momentum was, and then we'll figure out what an equation for the total final momentum is, and we'll set those things equal to each other. Take a second and see if you can figure it out.
So to solve this problem, what I'm going to do first is I'm going to write an equation for the total initial momentum and then an equation for the total final momentum. And I am going to set them equal to each other because, well, if momentum is conserved, and this is a closed isolated system, which it is, then they will be equal to each other. So let's go back to my diagram and let's figure out and use the same variables that are shown. So I'm looking at my diagram right now, and I have the momentum of the girl would be given by m subscript g times vgi. So that's the girl's momentum. And since I'm doing the total initial momentum, I'm going to add that momentum to the boy's momentum, mv times vbi. So this equation represents my total initial momentum. My total final momentum is actually zero. They were both at rest, so that total final momentum is equal to zero. Now, I know that the total initial momentum equals the total final momentum. This is the law of conservation of linear momentum. Since these two skateboarders are traveling along a straight line, then we are talking about linear momentum already. So I'm going to set these things equal to each other. We have mg vgi plus mv vbi, and that equals 0. Now I am trying to look for this velocity right here. So I'm just going to isolate this by subtracting this term for both sides and then dividing by mv. I'm going to double check, make sure I isolated that properly. So subtract this term, divide by mv. Great. And now I can go ahead and plug in. I'm told that the girl has a mass of 42 kilograms, the boy 51 kilograms. The girl is moving with a speed of 1.2 meters per second, and my diagram shows that she's moving to the right. So I have all my knowns, and I can go ahead and plug in. Negative, now we have 42 times 1.2 divided by 51. So I get 0.99 meters per second. That's actually 1.0, negative 1.0 meters per second. So I have a negative sign for velocity, which would indicate that this person's moving left. And if I look at my diagram, that is in fact the case. So 1 meter per second to the left is the final velocity of the boy.
One of the harder things about analyzing collisions sometimes can be actually writing out the equations. So I'm going to take a couple minutes and look at some different examples of collisions, and I'm going to have you guys try to guess what the proper total initial momentum equation is and the proper total final momentum equation. And this is going to be based on the variables that are shown in the diagram. All right, so let's first just get an understanding of what we're looking at here. We have m1, so some mass is moving with some initial velocity. This is before the collision, and there's m2 that has some also initial rightward velocity, but it looks like m1 is traveling faster than m2, which is why it eventually collides and it bumps m2 ahead of it, and so m2 then ends up with a faster speed. So we are trying to figure out which of these equations best represents the total initial momentum. And there's one that I hope is pretty obvious, right? And that would be option 4. So option 1, the total initial momentum, it would not make sense to multiply m1 by v2I, right? That's a nonsense answer, right? It's the momentum of m1 is given by the product of m1 times v1 initial. So this doesn't make any sense as a product. This equation down here that's shown as option 3, that doesn't include the momentum of ball 2, but ball 2 is moving, so it needs to include that. Option 2 right here says the total initial momentum equals their masses combined multiplied by some initial velocity. This equation here implies that they're moving with the same initial velocity, which they are not. This is sometimes the equation you would see for when objects are stuck together. Let's say I was running with a backpack on my back. You would add my mass to the backpack's mass and you would have our velocity shown. But that is not the case. They're moving with two distinct velocities, so it's got to be 4. So let's just double check. PTI, total initial momentum, is m1 v1 initial. Yep, that's the momentum of m1 plus m2 v2 initial. All right, this asks for the total final momentum. So we should again have m1 v1 final plus m2 v2 final, which would be option 2. So option 1 doesn't include the momentum of mass 1. Option 3 has them moving at the same final velocity, which is not true. Option 2 is the correct one, m1 v1 final plus m2 v2 final. Option 4 has their initial momentums added together, which technically their total initial momentum is equal to their total final momentum. So this equation might not be wrong, but it's definitely not the best representation of the total final momentum. Okay, we have a situation now with a clown that is being fired from a cannon. And we're asked which equation best represents the total initial momentum. So here we have m1 and m2 combined. They're at rest. So I would say the total initial momentum is 0. And then the total final momentum would be m1 v1 final plus m2 v2 final, which would be option 2. Okay, take a second, pause the screen, write out an equation for the total initial momentum here and an equation for the total final momentum as shown here. You should use the variables that are shown in the diagram. You know, I'm not even going to switch my cameras here. I think this is pretty straightforward. The total initial momentum would be equal to m1 times v1 initial. There's no momentum for the second car, so it's just m1 times v1i. The total final momentum would be just m2 v2 final, because m1 in the final situation has no momentum. This is actually a pretty common situation that's sometimes described as a fender bender, where you have a car rear-ending another car, and what can happen is it can transfer all its momentum into the car in front of it and push it forward. Okay, so knowing what we know now about how to write out the equations, I'd like you to try this problem. A 63-kilogram astronaut is on a spacewalk when the tether line to the shuttle breaks. So they were at rest, as in the astronaut is at rest relative to the spacecraft when the tether breaks. The astronaut throws a spare 10-kilogram oxygen tank in a direction that's away from the shuttle with a speed of 12 meters per second, and it propels the astronaut back to the shuttle. Tell me the astronaut's final speed after the tank was thrown. Pause here and give this a go.
I really like to have diagrams for these problems. I'm not an artist, so I am going to say that I'm going to call MA mass of the astronaut and then MT mass of the tank. So here they are at rest. And the astronaut throws the tank in a direction away from the shuttle. I'm just going to say that's to the left here. So we'll say VT, so the final velocity of the tank. And then that propels the astronaut forward. We're going to call that VA. So here are my diagrams. I want to find this speed here. So what I'm going to do is I'm going to write out an equation for the total initial momentum, that's 0, and one for the total final momentum, so MT VT plus MA VA. And now I know that this is linear, right? This is a long straight line. These things are equal to each other then. So 0 equals MT VT plus MA VA. And I have some knowns, which I should write down. Right, I know that the mass of the astronaut is 63 kilograms. I know that the mass of the tank is 10 kilograms. The speed of the tank is 12 meters per second, and that's to the left here, so that's how I drew it. At least you may not have drawn it to the left, and that's totally fine. If you drew it to the right and had it positive, you could still definitely get the right answer. And I'm looking for the speed of the astronaut. So I'm going to just isolate this guy right here by subtracting MTVT and then dividing everything by MA. So VA equals, we have 0 minus MTVT divided by MA. That is going to be 10 times negative 12 divided by 63, which is negative 120 over 63. So I have negative 1.9 meters per second as the astronaut's velocity. And you know, it doesn't make sense that I have a negative sign because this should be positive. So what did I do wrong here? I hope you guys can see my mistake. I have a negative sign here that I didn't carry through over here. Right? So it should have been negative 10 times negative 12, which would have given me positive 120 over 63, which would have been positive 1.9. And actually, this is, oops, what am I doing here? 1.90 meters per second, because I did have 3 sig figs for everything. Again, not that that's super important, but there we go.
Now, there's a couple ways to categorize collisions. We can call collisions as being elastic, which means that the linear momentum is conserved and also the kinetic energy is conserved. So kinetic energy is a concept that hopefully you've heard in chemistry class, as well as if you've taken physical science before. Kinetic energy is the energy associated with an object in motion, and kinetic energy is represented by the equation Ke for kinetic energy equals 1/2 mv squared. And this is an important concept. I will talk about finding the kinetic energy in a moment. But what we need to know at this moment is that elastic collisions obey conservation of kinetic energy. So momentum is always conserved. At least linear momentum is always conserved when objects collide. Kinetic energy is not always conserved. Sometimes energy can be transferred into other forms, such as thermal energy, right? If I rub my hands together, well, kinetic energy is being transferred into thermal energy, and that's why it's warming my hands up. Kinetic energy can also be converted into things like sound, right? If you hear a crash when a car hits another car, well, that's kinetic energy being transferred into other types of energy during the process of deformation when the cars collide. But elastic collisions, we say that kinetic energy remains constant before and after. So if we had a situation, for instance, here you have M1 colliding with M2, and before and after the collision, the linear momentum remains constant, and that's always the case with collisions. And it shows here that, well, the final kinetic energy is also equal to the final initial energy. So the kinetic energy of this guy plus the kinetic energy of this guy, that sum equals the kinetic energy of this guy plus the kinetic energy of this guy. It's inelastic collisions where kinetic energy is not conserved. So in this case, for inelastic collisions, kinetic energy is transferred to some other type of energy. And there's a special case for inelastic collisions where you have a perfectly inelastic collision where something sticks to the objects stick together after the collision. So think about driving your car and hitting a bug. A bug sticks to your windshield. That is a perfectly inelastic collision. Or think about a football player tackling another football player. That's a perfectly inelastic collision. When they stick together, it's known as being perfectly inelastic. And again, the difference between elastic and inelastic collisions is that for an elastic collision, kinetic energy is conserved. For an inelastic collision, kinetic energy is lost, some or all of it. Now, just like most things in science that we think of as binary, so one or the other, they actually, in the reality of it all, collisions really sort of exist on a spectrum where one end is elastic and one end is inelastic, and usually collisions lie somewhere in between, but it's really useful to be able to assume things are elastic or inelastic in order to make, simplified models that really do a good job of representing what's going on. But I should point out that, we can think sometimes a classic example of an elastic collision is a billiard ball hitting another billiard ball. And you see like very little loss of kinetic energy, but it does make a sound. So there is some sort of transfer of energy. So nothing's exactly elastic or inelastic, but there's some situations where it's, very little energy transfer. Anyways, why don't you guys try a problem, figure out what the type of collision that's occurring here is, and to do that, you would find the total kinetic energy of the system before they collide, and then find the total kinetic energy of the system after they collide, and compare. If they're the same number, well, that's elastic. If they're not, it's going to be inelastic. And again, the equation for kinetic energy is Ke equals 1/2 mv squared.
We have a 2 kilogram cart is moving 6 meters per second to the right on a frictionless track. It collides with a 3 kilogram cart that's at rest. So I'm going to call this M1 and V initial, and then we have M2, which is at rest. After the collision, the 2 kilogram cart that was M1 moves 1.2 meters per second to the right. So some smaller velocity. We'll call that V1 final. And then M2 has some V2 final that's larger than that. Okay, so I have my variable shown, and I should write out my knowns. M1 was 2 kilograms, M2 is 3 kilograms, V initial, that's for M1, is 6 meters per second to the right, so that's a positive 6 meters per second. And this was at rest. So here, V1 final is 1.2 meters per second to the right, and V2 final was 3.2 meters per second. So I want to figure out if this kinetic energy equals this plus this kinetic energy. So again, kinetic energy is equal to 1/2 mv squared. So here, I'll go ahead and find the kinetic energy before. So I'll call this initial kinetic energy. That's going to be 1/2 m1 times v initial squared, which is 1/2 times 2 times 6 squared. So that would be 1 times 36, which is 36 joules. That's the initial kinetic energy. My kinetic energy final is going to be 1 half m1 v1 final squared plus 1 half m2 v2 final squared. Oh, you know what? I put vector signs over it, but I'm squaring it, so even if it was a negative, it really doesn't matter. And plus, the actual equation's 1 half mv is its speed, but that's fine. So 1 half times 2 times 1.2 squared plus 1 half 3 times 3.2 squared. All right, so 1.2 squared is 1.44 plus we have 1.5, that's 1 half times 3 times 3.2 squared, which is 15.36. So off the bat, without even adding these together, I can see that kinetic energy was lost, right? Let's see, we have 1.44 plus 15.36 is going to give me 16.8 joules. And this is most certainly less than that. It's a little bit less than half of that, right? So this collision type is an inelastic collision. And if I wanted to find the change in kinetic energy, that would be Ke final minus Ke initial. It can be useful to find the change in kinetic energy often. So 16.8 minus 36, which would be 19.2 lost. So there was 19.2 joules of energy lost in this collision. And of course, by lost, I don't mean it disappeared. I mean it was transferred into a different type of energy.
So all this stuff is great, and useful, and hopefully you're understanding how to analyze situations where the objects are moving along a straight line. But in reality, collisions often happen in 2 dimensions. And so we can analyze collisions in 2 dimensions, but one of the things that's important to remember about doing that is that momentum is a vector quantity, and so vector quantities can be broken up into their x and y components, which make up that 2-dimensional vector. And we need to do this. We need to resolve 2-dimensional vectors into their x and y components in order to look at the momentum in each dimension separately, right? Just like, velocity and acceleration and displacement, the x and y components of those vectors are independent of each other. They don't influence each other. The same is true for momentum. So in each direction where the net impulse is equal to 0, momentum is conserved. So if you look at the situation here, we have a ball that is moving in this direction, right? That arrow right here indicates the momentum direction, which is the same as the velocity direction. So I know that this object's moving in this direction. And it's moving towards a green ball, which is moving to the right, right? So we can figure out from this after image that the blue ball hits the green ball, and now they move off in different directions. So if we know that linear momentum is conserved, then we know that the total initial x momentum is equal to the total final x momentum. And likewise, the total initial y momentum is equal to the total final y momentum. So when we analyze situations in 2 dimensions, we're going to need to break them up into their x and y components. All right, so let's end today's lecture with one final problem. A 1,600 kilogram pickup truck is traveling east at 20 meters per second when it collides with a 1,300 kilogram car traveling north at 16 meters per second. The vehicles remain tangled together after the collision. Determine the velocity, magnitude, and direction of the combined wreck immediately after the collision. I'd like you guys to try this problem first by drawing a diagram where you are labeling the masses and the velocities with different variables. Then list out your knowns that identifies what each of those variables stand for. You should then create a total initial momentum equation for the x, total initial momentum of the y, and same for the total final momentum. Then you can start solving for your unknowns. All right, go ahead and pause the video and you can let it rip.
So you'll see here that I drew a diagram of the situation before and after the collision. And I also listed out my knowns. So I want to note here that these two cars are driving perpendicular to each other. So we'll call this the x-axis and this the y-axis. And then after the collision, they stick together and move off at some angle theta above the x-axis. So my knowns are listed here. I have MP as the mass of the pickup. That's 1,600 kilograms. The initial x component of the pickup's velocity. That's what that big old variable, right? That, or I guess I should say long, right? It has a lot of subscripts here. It's v for our velocity. We have subscript pix for initial x component of the pickup. And that's positive 20 meters per second. It's in 20 meters per second to the right. There is no y component for the pickup's velocity. And then the mass of the car is 1,300 kilograms. The x component of the initial velocity of the car is 0, right? It's moving entirely in the y, which it's moving in the y with positive 16 meters per second. So our final velocity and our theta are our two unknowns, which means that we're going to need two equations, right, to solve for those two unknowns. So what I'm going to do is I'm going to apply conservation of linear momentum to the x direction and then also to the y direction in order to start figuring out what these equations would look like. So let me start with the x direction. So I'll say the sum of the momentum in the, or we'll say the sum of the initial momentum in the x is equal to the sum of the final momentum in the x, right? That's conservation of linear momentum. So now I'll plug in. The initial x momentum would be this car's x momentum plus this car's x momentum. So we'll do mp times v pix plus mc times v cix. And that equals the x component of this momentum over here. So that would be our pickup and our car. You know, we're adding the masses together first because they're going to be moving as one joined system. And we would multiply that by the final velocity times the cosine of angle theta. Now, a lot of these, not a lot, but we can obviously plug in values, and this, for instance, one of these guys is 0. Yeah, this guy's 0. So we can get rid of that term in a moment, but this is what our equation would look like. Actually, let's go ahead and just plug in our knowns right now. So we have 1,600 times VPIX is positive 20 plus 1,300 times 0 would be 0. And that equals 1,600 plus 1,300 times, this is our unknown, and our unknown here. Great. So, you know what? I'll simplify it even further. 1,600 times 20 is going to be, well, that's 32. So 1, 2, 3. And that equals 2,900 times v final cosine theta. All right, so this is what my equation looks like so far. I am going to, I mean, I guess I could simplify even further by dividing by 2,900, but I actually think there's an easier move when I look at my second equation. I'm going to have 2,900 again times some value here, so I might just leave this here for now. For my y direction, I'm going to say the sum of the initial y components of my momentum equals the sum of the final y components of my momentum. And then I'll go ahead and write out my equation again. So I have the mass of the pickup times the initial y component of the pickup plus the mass of the car times the initial y component of the car. And that equals their masses added together times v final times sine of angle theta. So this value now goes to 0 because you're multiplying 1,600 times 0. So we have 0 plus the mass of the car is 1,300. The initial y component of the velocity of the car is 16. And that equals, again, that's 2,900 times v final sine theta. So we'll multiply this out real quick, giving me 20,800 equals 2,900 v final sine theta. So I have these two equations, and I have two unknowns, right? V final and theta. And I'm going to try to simplify even further. I'm going to try to use some algebraic methods I can to start figuring out what each of these things stand for. Now, I can divide out 2,900 times v final. They're on both sides. So actually what I'm going to do is I notice that sine theta, if I divide this equation by this equation, I'll get sine theta over cosine theta, which is equal to tangent theta. And then it will also cancel out these values, which would be useful for me. So I'm going to go ahead and divide this by this. So these cancel, and I get 20,800 divided by 32,000 is 0.65 equals the tangent of theta. And so now all I need to do is take the inverse tangent of both sides. To get theta alone. So the inverse tangent of my answer gives me 33 degrees. So now I have one of my unknowns, and I can use that, plug it into one of these guys to solve for v final. And I should know that this is 33 degrees above the positive x-axis. Okay, so let's plug in. I'm just going to take this equation here, since it's easy to use, and you can see it on this kind of limited screen here. Limited screen space, I should say. So we have 20,800 equals 2,900 times v final multiplied by the sine of 33 degrees, which means v final is going to equal 20,800 divided by 2,900 times the sine of 33. And I got 13.169 or 13 meters per second. I'm just checking my work real quick, making sure I did that right. And I should also check and see if that's reasonable in a moment. So I said 13 meters per second. I'm at an angle of 33 degrees. So my v final, my final answer is 13 meters per second at an angle of 33 degrees above the positive x-axis. And, I just said I should check to see if that's reasonable. And what I mean by that is, we should expect that value is less than these cars were moving at, or at least that this car was moving at. You wouldn't expect that these two things clash together. We have a larger mass and then a larger velocity too. That wouldn't make any sense. So far it seems reasonable. I can go back and check for minor errors, but I actually feel pretty comfortable that that is my answer. Thank you all for tuning in, and I will see you soon.